All right, today we're diving into something huge. We're talking about a massive shift in the world of engineering, a move away from the rules that have guided us for centuries and into a totally new data-driven world. Let's jump right in.
So, for hundreds of years, engineering has basically been about one thing, right? Applying the laws of physics. But what happens when things get messy? I mean, really messy. Trying to predict something as wild as turbulent fluid flow, or juggling the insane demands on a smart energy grid second by second. Our classic equations, they kind of start to break down.
And this really gets at the heart of it, these two different worlds of engineering. On the one hand, you've got your first principles models. Super elegant, right? Think Newton's laws telling you exactly where a rocket's going to go. It's predictable. But then you have data-driven models. These don't start with an equation. They start with experience. Imagine looking at data from thousands of rocket launches to spot tiny patterns that the perfect equations just couldn't see. It's a totally different ballgame.
And the engine driving this whole shift, it's machine learning, plain and simple. We're talking about a massive pivot, moving away from systems built on perfect, theoretical equations and moving towards systems that actually learn from what happens in the real world.
Okay, so when we say a machine learns, what does that even mean? Well, this is the classic definition from computer scientist Tom Mitchell. It's basically the foundation for this whole field. Now, it looks a little academic, I know, but trust me, it breaks down into three really simple and important ideas.
Let's unpack that. First, there's T for task. That's your goal. What are you trying to do? Let's say, spot a fault in an engine. Simple enough. Then you've got E for experience. This is the data you feed it, maybe thousands of hours of sensor data from that engine. And finally, P for performance. How do you know if it's doing a good job? Well, you measure it, maybe by how accurately it predicts those faults. And here's the magic. If its performance gets better the more experience you give it, boom, it has learned.
Right, so you can't just say, I'm using machine learning. That's like a carpenter saying, I'm using a tool. Which one? It's really a whole toolkit with three main ways, or paradigms, that a machine can learn.
First up, and probably the one you hear about most, is supervised learning. The best way to think about this, it's like studying for a test with the answer key. You show the machine tons and tons of examples where you already know the right answer. These are your labeled input-output pairs. It just learns to connect the dots. It's perfect for things like predicting when a material might get tired and break, based on a whole bunch of stress data we've already collected.
Then you've got unsupervised learning. Now this time, we take away the answer key. There are no labels. You just dump a massive pile of data in front of the machine and say, find something interesting. It's all about finding hidden structures on its own. Things like automatically grouping customers into different segments. Or, and this is a big one for engineers, spotting a really strange, unexpected reading from a sensor on a power grid that no human might have noticed.
And number 3 is reinforcement learning. This one is super cool. It's basically learning by doing. It's trial and error on a massive scale. You have an agent. Think of it as a robot or the AI in a self-driving car, and it just tries stuff out in its environment. When it does something good, you give it a reward, a virtual pat on the back. When it messes up, it gets a penalty. And after doing this millions or even billions of times, it figures out the absolute best strategy to get the most rewards.
Okay, so that's the theory. Super interesting, right? But how does an engineer on the ground actually use all this stuff? It's not like you just sprinkle some AI dust on a problem. No, it's a very deliberate, structured process. It all kicks off with really nailing down the problem you're trying to solve. Then, and this part is absolutely critical, you've got to gather and clean up your data. Garbage in, garbage out, right? Once you've got good data, then you can pick a model and start training it. After that, you have to test it like crazy, see how it holds up on data it's never seen before. And if it passes, you finally deploy it into the real world. But you can't just walk away. You have to watch it, monitor it, make sure it keeps performing. It's a full-on engineering pipeline.
And here's the thing you really need to get. This isn't some niche workflow for a few tech companies. No way. This data-driven approach is shaking things up everywhere. It is fundamentally changing how engineers solve problems across literally every single field.
And just look at the sheer range of this stuff. It's incredible. In civil engineering, we're talking about using sensor data to predict when a bridge needs repairs before something catastrophic happens. Mechanical engineers, they're using it to listen to the tiny vibrations in a machine to catch problems early. Electrical engineers are forecasting a whole city's power needs to make the grid smarter. In chemical engineering, modeling complex reactions that used to be impossible. This isn't some futuristic wish list. This is happening right now, today.
But look, with all this incredible new power comes, well, a whole new can of worms. It introduces some really tough challenges, and honestly, a whole new level of responsibility that lands right on the engineer's shoulders.
Yeah, the hurdles are pretty significant. First off, just getting your hands on enough good, clean data can be a nightmare. Then you've got the famous black box problem. The model might be right. It might tell you a part is going to fail, but it can't tell you why. And if you're talking about an airplane part or a medical device, just trust me isn't good enough. That's a huge safety issue. And it all comes down to this. Making sure these models are tough, reliable, and safe in every possible situation, that's not just a coding problem. That is a fundamental engineering responsibility now.
And that really brings us to the bottom line, doesn't it? The job of an engineer has just gotten bigger. It's not just about building things that work anymore. The new challenge, the new mandate is to build intelligent systems and to build them responsibly.
This quote really just nails it, I think. It says machine learning isn't just another computational tool. It's a whole new paradigm of engineering thinking. It's not just a new wrench in the toolbox. It's a completely new way of looking at the toolbox and the problems you're trying to solve with it. So that leaves us with this pretty wild question to chew on, right? If data is becoming just as important as the laws of physics, what does that mean for the engineer of the future? Are they going to be more of a data scientist than a physicist? It's a huge question, one that kind of redefines what it even means to be an engineer. And it's something the next generation is going to have to figure out. Thanks so much for joining me.